So actually, I will share a screen because I did prepare a set of slides. And in your case, because you're starting, probably the first slide will be the most important, not this one. This is the title. But actually, how do you do a career in science? And the problem is that it's not easy to plan it. And this is what I want to emphasize in here. So this is a map of the world. And just to emphasize how my career has been. So I was born, a tiny little baby, in Santiago, Chile, of all places. I stayed there until I graduated more or less at the level of university with my chemistry. And I went to Florida, did my PhD. After that, I moved to Switzerland. I did my PhD, my postdoc at the University of Geneva. After that, I stayed in Switzerland. I work at Nestle. So I work in industry and in between, just keep in mind. And actually, it was during my time in industry at Nestle that I started working on aging. But industry was not for me. So I came back to the States as a faculty, as an academician. Okay, after a while, I decided to give it a try and go back to Chile, again as a faculty. That didn't work, primarily because I didn't get along with my family. So I came back to the States, now at the NIA, working as an administrator first, and then I became director of the division of the aging biology. I retired from that about a year ago, a little bit more. And my latest move has been to move to Toulouse in France. So what I'm trying to emphasize in here is you don't know what's going to happen. You just can't plan it. You just go with the best you can at any given stage and do the best you can. Do the best you can, and then opportunities will arrive if you do a good job. You're going to be offered a possibility to flourish somewhere else. At this point, I'm considering another move. But I'm not going to go into that because it's not that. So this is the point I want to make about career. I stayed in science always. I studied biochemistry, but I don't remember the curve cycle whatsoever. I mean, you move along and you use what you learn to help you. What I would like to talk a little bit is what I've done during my time as director of the Division of Aging Biology at the NIA. Of course, I was involved in a lot of different things, but there's three things that I'm particularly proud of. One is that soon after I became director, so 2007, 2008, I introduced into the field the concept of Healthspan. We were always talking about lifespan before. This was not easy. The people did not want to do it. But right now, you can't get away from talking about Lspan if you're working on aging. Then 4 years later, I came up with this concept of geoscience, which is what I will be talking for a few minutes after this. Lately, 2018, I tried to introduce the concept of molecular resilience, and I'm not going to talk about that. That one I have not been able to push as much as I wish I had. But it's a concept that's out there. Some people consider it as important, not at the same level of Healthspan or geoscience. So let's talk a little bit about what geoscience is. This is a background. So we can't deny that improvements in health were a great achievement in the 20th century. We improved our health tremendously, we improved our lifespan. Everything has been great with what we managed to do in the 20th century. But we have to consider that the major problems at that time were diseases of simple etiology. Basically, they were external organisms attacking us. And we were able to solve that by improving public health services, vaccination, sanitation, etc. And that was enough because the enemy was external, right? But we have to understand, and this is critical for the future of medicine and health, that this will not work against the chronic diseases of the 21st century. simply because it's a different situation. Now the enemy is within. It's your body that fails to adapt to the environment. And this is what causes the problem. So the major risk factor for these chronic diseases is aging itself. It's something within you. You cannot attack it with an antibiotic or with things like that. And here's the real issue. We go to the doctor when we get sick. And for one thing, we should know. We should go when we're healthy. I really, really want to focus things on health and not on disease. But you go when you're sick. That's the bottom line. And the doctor looks for symptoms of one disease or another. Right? Depends on your symptoms, starts looking for something. And classifies the disease. Now, each disease, disease 1, has its own physiopathology. If you have high cholesterol, it's a cardiovascular disease. If you have high glucose, then it's diabetes. If you have amyloid in your brain, it's Alzheimer's. But that's a small part of what drives that disease. What drives the disease really is aging. It's a main risk factor by far. And I'm not going to go into the details because I don't have the time, but it's by far the main risk factor for any chronic disease is aging itself. So this is where the concept of geoscience comes. If aging biology is the major risk factor for not only for disease 1, but also for disease 2, 3, 4, 5, 6, etc., then we should attack aging biology. We should attack this instead of the physiopathology of each disease at a time. Attacking cholesterol will get us only so far because you're going to avoid cardiovascular disease, but you're going to get Alzheimer's. What's the problem? Right? Well, if you attack neuroscience, this is a concept. And if you attack if you attack aging, if you make aging go at a lower rate, you're going to reduce the rate of appearance of all of those diseases, not just one at a time, but all of them at the same time. And not only disease, but also other things that happen with aging, like frailty and fatigability and things like that, that make our quality of life go down. All of those things are driven by the aging process. Therefore, attacking aging will give us a better outcome than attacking each disease at a time. Now, this might sound like a pie in the sky, too much daydreaming there, okay? But it's not so bad. Actually, what happens is that major determinants of biological aging have been identified. You might have heard about the hallmarks of aging published by Lopez-Otin and the pillars of aging, which is a parallel paper that we published from our geoscience interest group in Cell in 2013, 2014. So major biological determinants of aging have been determined, and attacking those determinants has shown us that aging is very malleable. We can change the lot, and we can do it by behavior, like dietary restriction, by genetics. There's hundreds and hundreds of genes, and the combination of studies in genetics and calorie restriction has allowed us to identify a handful of drugs, which we call geroprotectors. Drugs that attack aging, not a particular disease. And by doing that, delay the aging, the disease process. This works very well in animal models. We have tons of studies showing geroprotectors modifying the hallmarks of aging and having improved health. And some studies in humans are being done now. They're in their infancy. They're phase 1 studies. They're tiny, but they look promising. And that's the main thing that I want to say. So this is a very short thing. Responding to Samantha, what distinguishes geroscience from geriatrics and gerontology? So geriatrics is taking care of old, sick people. Gerontology is studying why they get sick and old. Geroscience is using basic biology knowledge to prevent them from being old and sick. So it's a preventive strategy. We want to treat the ones that get sick, certainly, yes, of course. but the goal is actually to prevent it, to keep them from getting there. So just the last slide here, just in case, I know some couple of people here, but just in case anybody wants to ask any questions about getting research funded, this is what I've done for the last 17 years of my life, actually. Working at the NIH, I was in charge of funding people working in this field. And there's a lot of things to be learned about how to get your ideas funded. So if you have any questions on those topics, please feel free. And I will stop sharing now, and I'll take your questions.
And so I think I was in the room with a few of you earlier. Feel free to throw questions into chat or to unmute your microphone or your camera, and you can ask Dr. Sierra questions about the concept of geroscience, where he came up with it, and or anything else about getting your research funded. And perhaps,
any questions?
Perhaps you can ask a question of the folks who are in the room about what interests them most about the aging field and where they are in their careers. So,
Yeah.
Shufeng, we heard earlier from you that you are you just graduated from undergraduate and are interested in this field. So we're excited to have you. I'm not sure who NCCCMR is, but if you could share with us what you might be interested in terms of aging research.
Yeah, I guess I got to my questions first. So the geroscience just looks it's like a dream. Does it more like a dream or a future where we are going to approach?
Yeah. As I mentioned, it is, people think that it's a little bit of a dream. Yes, that's why I meant a pie in the sky. That's the expression that we use to say this type of thing. But it's not. It's actually the time. I have to say that, so Samantha was talking about how I came up with the idea. It's just the classical example of being at the right place at the right time. The field was maturing so fast. We were learning so much about aging biology, which was the topic I was interested in for my entire career, as I mentioned, that it gelled into that, and I happened to be in the right place by being director of the division that I was able to promote it.
And so according to what you have talked to us, so is there a certain a center of the net in the whole mechanism of the gerology, I guess? Is that the word?
Sorry, what do you mean by a center?
You know, it's a big system. The habit of the getting old, getting aged. It's a big system of bioprocess, I guess.
Yeah, I'm not sure I understand exactly what you're asking, but if there's a system that we understand by which we get aging, is that what you're asking?
No, something like a hinge or a pivot.
Okay. So
that we can
for studying it or to fund it.
Simply target at. Is there a certain thing? Is it possible that we can find it in the future, or we still have to deal with a huge system, a huge network, and we have to choose different spots to deal with them, and when they are all accumulated, then we solve the problem of the gerology. Which one do you think?
I'm not 100% sure I understand what you're asking, but there is a lot of interest right now in industry, in biotechs, in companies. There's centers being formed all over the world. In fact, that's what I came to Toulouse to do. There's a center being formed in here. We're gonna build a building for geoscience. That's happening all over the place. There's a lot of interest from biotech. You might have heard recently the founding of a big company by Bezos. The interest in those companies usually is on longevity.
Yeah.
And in my mind, that's not the right thing, because longevity is not what we really want. I don't want to live forever. What I want to do is live in good health, to be happy forever. Yeah, that I would like. But there is a lot of interest and a lot of push in the field, and from new people coming into the field. Actually, the field is growing at a rate that I cannot keep up with right now. There's a lot of opportunities for you, for example, to pursue your future studies, to move further in this field. There's a lot going on.
Okay. Let me try to ask in another way.
How about if you write it down?
Write it down.
Yeah, in the chat. Yeah.
Okay.
And in the meantime, we can ask Anna what she does. Anna.
Yes. Hi. Very nice to be here and to hear you speak. I'm sorry I joined a little bit late, so I only caught the last bit of the presentation.
You missed the best part.
Sorry.
My personal history.
I did read your bio though, so I think I caught up. So I'm an assistant professor currently at the University of Connecticut. So I'm a computational biophysicist by training, and I'm doing work kind of at the smallest scale. So looking at molecular mechanisms associated with different systems. With respect to aging, I'm interested in extracellular matrix components and their the progression and change in their structure and function in aging and disease. And actually, last year we submitted an NIH grant, or NIH proposal. It was reviewed, probably not funded based on the numbers. So I wanted to ask you, just for any kind of general advice you might have for an assistant professor applying for an R01, because I know, the NIH is typically funding more senior investigators.
No.
Okay.
No, we fund people at all. In fact, we fund undergraduates and we fund at all levels. It is true that it's a little bit when you are applying for an R01, it becomes kind of competitive, and you're indeed competing with Nobel Prize winners. Yes, that is true. Nothing we can do. However, we also have these early stage investigator things that within a certain number of years you can get that. Mm-hmm. So all I can say is keep trying, but more important than that. So you submitted to the NIA or to another institute?
To NIA, yep.
And you tell me who was the program officer?
Candice Carr.
Candice, okay.
Yes.
Okay. So you had a good conversation with her?
So we haven't spoken yet actually about the proposal because we're still figuring out how to revise it, and I want to kind of keep those ideas before we speak.
So that's my main advice to you is that you have to understand that at the NIA, our one and only role is to give you money. That's what we do. Okay? We can't give it to everybody. There's not money for everybody. But that is our role. This is what we want to do. So our goal is to help you. And you should really call your program officer early on and discuss with them. And once you get the summary statement, discuss it with them, because we have looked at so many of them that we know how to analyze them. And one thing that I always point out, for example, just to give you an idea, sometimes somebody gets a summary statement, and they seem to be nitpicking. Nitpicking. Reviewer 1 didn't like it because of this, and that. And reviewer 2 didn't like it because of that and that. Different things.
Mhm.
And the applicants try to respond to all of those. That's a mistake. That makes a mess of the proposal. It becomes completely unfocused.
Mhm.
When the summary statements are like that, what happens is they didn't like the idea. And they're trying to justify their bad score by picking on this or that or that. And different people pick on different things.
Mhm.
So you don't gain anything by responding to them,
Mhm.
right? You have to change the way you propose the idea. So these are the large things that can be critical for you to move forward. So since there's only 2 of you, I will offer you that if you send me your summary statement, I will help you too.
I really appreciate it. I'll do that. Yeah, I'll
Yeah.
send you my summary.
Because actually, I was there for 17 years. I can help you, and
Yeah.
actually, I can help you with things that Candace is not allowed to.
Wonderful, wonderful. Happy to hear your advice. That would be great.
Okay, let me read what Shiveng says. Okay, based on the methodology of medicinal science, we need to find certain targets so that we can find the therapy. Will there only be a small number of core targets, or will we still have to deal with a large network composed of many targets? Very good question. Thanks. Now that I understand it. So basically, the number of targets that we have now, it is a handful, 7 to 10, something like that. I mean, different people have different ideas, of course, but basically both of the papers I cited, the one by Lopez Otin and the one by Kennedy, in which I'm a senior author, we identify 7, they identify 9, okay? And neither one had another one that has come in between, which is the microbiome. So let's say it's between 8 and 10 right now. But it's more, I mean, I'm sure more will appear, just like microbiome appear in between. We didn't know that 10 years ago. Okay, so it's not there. It was not in the, nobody was thinking about that. However, one thing that's very, very, very important that is happening right now is that we're finding is that these things interact with each other, basically, and in a positive way. One thing that is, to me, has been amazing is that when you develop a drug against the disease, say statins against cardiovascular disease, what's your main concern? Is that it's going to have negative effects on other organs, right? That's the main thing. That's the main concern about developing drugs. What we're finding is that these hallmarks of aging interact in such a systems biology manner that when you improve one, all the others improve too. So it's the opposite. Instead of having that you improve one and you have a problem with another, no, this is the other way around. You improve one and the other ones improve at the same time. So you remove senescent cells, for example, and your proteostasis gets better. Or the other way around. You improve proteostasis and you get less senescent cells and you get less inflammation and they interact. I think that's the coolest area that's coming up right now is how do these things interact with each other? Is there a certain priorities of some of these hallmarks being more important than others? Is there priorities in terms of diseases? In other words, for example, if we think about Alzheimer's disease, we know that proteostasis and inflammation are going to be the major ones, right? We know that. But maybe we can move something else and fix DNA repair, and that will improve proteostasis. There's a lot to be done in that. Does that answer your question a little bit better than before? Do you think? Yeah. Okay.
Yeah. Thank you. Thank you. Yeah.
Sorry, I could not understand it properly before.
Yeah. Thank you. Thank you very much.
All right, so Janssen?
Jung-soon, if you're able to ask a question either through the chat or by turning on your camera, you should feel free to. Dr. Sierra has gone through and as you're typing, I will try and summarize his main points for us. Oh, I'm sorry about your technical problems.
Technical problem, yeah.
But
Happens.
the good news is that it's allowing us to meet from across the world, which is wonderful.
Yeah.
And so Dr. Sierra was providing us with some of his personal background and his story for how he got to where he has been. And he taught me about the difference between geroscience and geriatrics and gerontology, which was really helpful, and has also been sharing with us how aging biology is not necessarily the idea of needing to look at a disease at a time, but more holistically at how you reduce aging. And so that way you can live healthier, longer lives at the same time, as instead of trying to piggyback multiple diseases that will then lead to other problems down the road in terms of people's functional well-being.
One thing that I always emphasize, by the way, is that I don't give a damn about any disease. You talk to me about cancer. Cancer is just a little problem. It's just a little thing that happens during aging. Alzheimer's, the same thing. It's just part of it. I don't care about diseases. I care really about health. I want people to be healthy, not just to not have disease, which also comes with a side that's socioeconomic and so on. That's a completely different story, but it's also important.
So Jung-soon, if you have any specific questions for Dr. Sierra, please feel free to ask it to him directly. He's offered Anna to help look at her comments from a proposal she submitted to the NIH. And he is a wealth of information and a wonderful person.
So maybe could I ask another quick question?
Yes, please.
This is more about maybe your career trajectory. So what would you say was your favorite and least favorite thing about working for the government?
My favorite thing is that you have a lot of power, a lot of role to play in the field. You are directing the field, indirectly, of course. I mean, it's scientists that drive the field, but you are helping guide things in one direction or another, as I mentioned, you missed it. So basically, the first thing I did once I became director of the division was I introduced the concept of Healthspan. That was unheard of before. And my issue was, no, we don't want to live forever. We want to live healthy. So let's measure Healthspan. People fought me because they said, that is such a fuzzy thing. Lifespan is easy. The animal is alive or is dead. Easy. Health, am I healthy? I don't know. I have a little headache today. Am I healthy? It's more difficult to measure. However, I managed to convince the field. So now everything is about Healthspan. Then I came up with the concept of geroscience, and I have to say, there again was a lucky being at the right place. I was able to push it because I was the director, because I controlled the money. It's that simple, right? So it gives you a lot of satisfaction from that perspective. What I didn't like very much is that there's a lot of red tape, a lot of things that you cannot do, right? I was a little bit unusual in a sense because I kind of rebelled against it, and I ended up doing a lot of things that my boss kept looking at me like, why are you doing that? Because I want to. but there's a lot of limitations on what you can do. You cannot just publish a paper, for example. No, you have to have permission, because that paper represents the view of the NIA. So you cannot just put up your idea out. No, it has to be approved by the upper echelons. So that's a little bit limiting. But all in all, my time at the NIA was fantastic. I mean, I would certainly promote people doing that because it's really a fantastic job. You're directing the science. You're allowed to think big. One thing that I always say is one of the things we do. It's not a lot, but we do put RFAs, as you know, request for applications. So the way I say it is, when I was working in the lab, if I had a good idea or bad idea, my role was to convince my students and postdocs to actually do the experiments. Now, if I have an idea, I have to convince only one person, Richard Hollis, the director. He gives me millions of dollars. And then I say, who wants to do my experiment? And I get Nobel Prize winners applying to do my experiment. Good postdocs. Yeah. Right? So there's a lot of good things about that. So I really enjoyed it.
Yeah, that's a very
Oh,
interesting perspective.
there's Young-Soon was writing. You mentioned that you want to focus on Healthspan. I really agree with your point. We will expand longer lifespan, but if we have sick, it doesn't help. Absolutely. That's precisely the point. I had a long-time question about calorie restriction extend lifespan, but if we lose our muscle, we'll have problems. Also need to worry about osteoporosis. What do you think about we need to maintain our muscle mass and health span from our view of longevity? Correct. You're absolutely correct. Calorie restriction produces a lot of positive things, and you're pointing out some, the musculoskeletal problems. Yes, there's other that people don't realize, which is probably is a much more interesting situation. We have known for a long time that calorie restriction improves your immune system. Okay? That happens not to be true. It happens that once you take the cells from the calorie-restricted animal and you put them in culture, being fed normally and in good environment, they work better than the controls. Yes, that is true. However, if you actually infect an animal with a virus or a bacterium, they die. They become much more susceptible. Why? Because they don't have defenses. They don't have something behind themselves to increase their defenses. So calorie restriction is definitely something to be used as a model for studying in the lab. That's how we learn a lot about aging. I really like the model of calorie restriction. However, as you point out, it's not for humans. It's only for studying. It's a model. Okay, it's not for humans for one thing because it's very difficult to do. Hey, I live in France. I'm not going to do calorie restriction. The food in here is fantastic, right? That calorie restriction is not easy to do, right? Now, there's new modalities that have come, which I think are very interesting. The time-restricted thing, for example, that I do. Actually, I do it. I think it's a different modality where I don't have to keep myself from eating. I just have to control the time when I eat. Scientifically, it's more solid, okay, and it has more possibilities. Now, in terms of the side effects on cardiovascular, in musculoskeletal issues, as you point out, probably won't happen because it's isocaloric. I'm taking the same amount of calories I would take normally. It's just that I take them at a particular time. So there's these are things that are being developed, and like everything else, you come up with a great idea. Yeah, it increases lifespan and health span in many aspects, but it doesn't work on everything. So you have to take it with a grain of salt if you want to apply it to humans. And we have to do studies. So there is this big study called Calgary, where they do show good results. Indeed, bad things on the bones and the muscles. Yes, that is correct. The same is true for by the way, if you give rapamycin, it has bad effects on muscle. So those are things that we're studying. There are going to be side effects that we have to take into account. So you got something else. I thought we had calorie restriction effect well from animal models and primate studies, controversial data. And in Wisconsin, do you think we have better model for Lspan to study? Okay, let's go first into the controversy between NIA and University of Wisconsin. Actually, the people from both labs got together. We got them together actually at the NIA to discuss this. They both agree that calorie restriction in their primates improved health span, improved health. What they did not agree was whether it had an effect on lifespan, and that was because the studies were not meant to be parallel. They just happened to be similar, but they were not exactly the same, so they had different parameters, different ways. For example, I mean, the most best known things that in the case of Wisconsin, they were treating endometriosis, which is a common thing that happened in these monkeys. In the NIA, they were not. Why? Because the University of Wisconsin was trying to mimic what happens in humans. So we treat diseases. In the NIA, they were not. They were trying to mimic the mouse studies. So they were not treating. So that led to the difference in final outcome in terms of lifespan. But in terms of health span, there's no question that both of them found positive effects in most systems except musculoskeletal. So do we have better models to study health span? That's a difficult question. I think the most exciting model that we have right now is the dogs. I don't know if you're familiar with this study run by a group at Seattle, where they're taking your pet dog, the dog that you have in your house. So for one thing, we're not going to do anything bad to it. that's for sure. But we're going to analyze them over time to see what how they age compared to us, because they share our environment, they share our food, they share everything with us. So I think they're a very much better model as long as you don't want to do anything bad to them. If you're gonna try to induce cancer in them, no, I don't think the owners will want to do that, right? But if you want to try a geroprotector, so they're trying, for example, with rapamycin. If you want to treat them with a geroprotector, and you tell the owners, well, you know, in mice we have not seen anything negative, and they live about 20% longer in better health. We like to try. 100% of the animal owners will say, yes, I want that. We all want our animals to live longer, right? So, yeah, so mice and negative. Do you think this is come from the muscle? What do you mean by mice and negative? I have to say, I used to have a slide that across the slide like that, it said, death to C57 black 6 mice. We have put way too much emphasis on that model. It's a model that doesn't develop some of the diseases that we're interested in. So now you're coming to what you really want to ask, native than human data. So you think, what can we do in humans? There's a lot of things we can do in humans, but not everything. You cannot try a geroprotector in humans if you have not tried it in an animal model, or 2 or 3. So to try to implement pharmacological treatments, you need to continue studying animal models. Now, there's a lot that you can do with humans, much more than when I was in the lab, because with the advent of omics, there's a lot of questions you can ask now without being too invasive. However, if you want to study how your brain ages and you need to dissect the brain, you're not going to get many volunteers. The mice, yeah, we'll get their brains. They have nothing to say. So the bottom line is, and this is true in research in general, you have to balance a lot of different things and choosing your model is one of the most important things. Choosing your model carefully to have a model that addresses the type of questions that you want to answer. And there, for example, I don't know if any of you work with C. elegans, and if I insult you, please, I'm sorry. But C. elegans, for example, we have used that as a workhorse in aging to death, literally, because we were for them today. So C. elegans was developed by Sidney Brenner because they're transparent and because their genetics is very easy to do. Those are the advantages of C. elegans. If you try to do Healthspan in C. elegans, I think you're pushing. Yes, it can be an idea if you're making them swim or whatever, and you're measuring different aspects of health. Yeah, it can give you a hint, but at the end, they're so similar, so different from humans that if you're going to measure health, I think you're better off with a better animal. But I think it's important to choose animals that develop the diseases that you're studying, if you're studying disease. And if you're studying aging, do it in aged animals. That's another poem that I have. Everybody has heard, how many times have we cured cancer in mice, but not in humans? Well, first of all, we have made a lot of progress with humans, if we get that, right? But it's also, why is that? Well, all the studies on cancer are done in 3-month-old mice. 3-month-old mice don't have the same physiology as a 24-month-old mouse. So to me, you can study whatever you want. If you want to study if your protein gets phosphorylated in CD67, or if your protein interacts with this other protein, fine, do it in a young animal, do it whatever, I don't care. But the moment you use the word translation, you have to do it in an old animal. Otherwise, it's not going to translate to the real human population that you're addressing because they are old. So they're different. So choosing your model, very, very good.
Thank you so much for answering those questions, Dr. Sierra.